All right, everybody. Welcome back to our next lecture video. This is lecture video number 3 for chapter 10 here. All right, talking about, firstly, something called molecular geometry. Now, we've obviously spent a lot of time talking about Lewis structures recently, right? And although that's not entirely going to change, we're just going to kind of use what we know about Lewis structures to help us kind of define some of the look of the structures that we've been building, right? So we've been taking time to learn how to build the things, but we haven't really taken the time to look at what we built and kind of give it some defining characteristics. And that's exactly what molecular geometries do. Now, molecular geometries are under this umbrella called VSEPR theory, which is short for valence shell electron pair repulsion, right? Lots of fancy words there, but long story short, basically VSEPR theory is used to predict three-dimensional shape of molecules. That's it, right? Because, guys, although we've spent an exorbitant amount of time drawing out Lewis structures and learning how to put them together on paper, they're not three-dimensional, right? Molecules are not three-dimensional, or not two-dimensional, right? They're very, very, very three-dimensional, right? So they're not just the 2D kind of image we've been drawing on our pages, right? They're very three-dimensional. And that's kind of the purpose of that covalent molecules lab that we did recently, right? Building those molecules and looking how they look sort of arranged in 3D space. And that's exactly what we're going to be doing, talking today about this molecular geometry stuff. Now, also on top of that, getting through today's material here in this lecture video is going to be our opportunity to finalize our covalent molecules lab, right? Remember how I mentioned that in the center of our data table, all those extra parts to our data table, things like nonpolar versus polar, molecular geometry, bond angle, all of those things there, right? Those are going to all be solved and answerable now after today's video. But we'll talk more about that in class, okay? Well, how do we do that, right? How do we go about defining some of the characteristics of our geometries, the 3D makeup of our molecules here? It's pretty easy. First and foremost, draw the Lewis structure, right? So it's no wonder we've spent so much time talking about Lewis structures and how to draw them, how to build them, all the good stuff, right? The second thing is to do what's called count the bonding domains and non-bonding domains on the central atom, okay? Now, you're going to probably ask yourself the question, well, what if there is no central atom? Then this stuff doesn't matter, and I'll kind of show you an example of that in class when we actually start to tackle this stuff and do some sample problems in class together, okay? But this is pretty specific to molecules that have a central atom. If they don't, again, there's another case scenario that we don't have to worry about until we talk about it. And then use the table to determine the shape. Well, what table am I talking about? I am talking about none other than, and I'm going to come back to this page in a second, this table right here, okay? This table is present in your reference tables. That's at the very, very, very back of the reference table. It's the very last page, the last set of tables. It's actually, titled table number 1, right? So if you're looking for table number 1, it's the very, very back of the packet, page 13, towards the very, very back. Okay, now, what about all this stuff here, right? How do we continue to actually do that, right? How do we use this table? It's pretty straightforward. Now, going back to what I mentioned about how, if there is no central atom from over here, this kind of helps explain that right away, okay? If there are only 2 atoms in the Lewis structure, then the geometry is always linear, right? So, for example, let's think of some examples that we've done recently where there's only been 2 atoms in that structure, right? Thinking about something like O2, for example, or N2, right? Or something even as simple as CO, right? These are 3 examples of covalent molecules that only have 2 atoms in their Lewis structure, right? 2 atoms of oxygen, 2 atoms of nitrogen, 1 atom of CO, 1 atom of oxygen to combine for 2, right? So if there's only 2 atoms, they always come out what is known as linear, okay? Well, if that's not the case, then we have to kind of diverge from that a little bit. But if they're linear, that means their bond angle is 180 degrees. Well, if I can explain that for a brief second, let's say I've got this model here for, let's do oxygen, right? Oxygen's a pretty simple one, right? Oxygen is double bonded to another oxygen with 2 dots here, 2 dots here, 2 dots here, and 2 dots here, right? This is the Lewis structure for a O2, right? For O2. Now, if I were to draw this in terms of like a line, this is what the line would be, right? And if I had to determine what the bond angle was, right? Bringing it back to some geometry here, I'm sure everyone's favorite math class, right? The angle for a straight line is 180 degrees, right? So just like the sort of structure of this is linear, the bond angle, the angle between the 2 atoms for that particular bond, and I kind of overdrew that, the angle between these two atoms here in this bond is 180 degrees, right? Just like a linear straight line. Okay, that's essentially what this is saying now. Now, to make things a little bit more complicated, what happens if we have more than two, right? We've got three or more. Well, that's where the central atom comes into play. Now, first things first, we have to be able to define what a bonding domain is and what a non-bonding domain is, right? Because that was one of the big things. If we go back a couple here, it says count the bonding domains and the non-bonding domains on the central atom. Okay, and it's specific to the central atom. So how we do that? Very easily. A bonding domain is a bond to another atom. That's it. Okay, just any bond to any atom ever around the central atom specifically. Okay, so if I look at a single bond, that's going to count as one bonding domain because a single bond is just a covalent bond. And now you're probably thinking to yourself, well, if a single bond is one, isn't a double bond going to be two? No, it's actually going to be one, right? Because a double bond at its essence is just a bond. It's a bond between two atoms, right? So any given bond between two atoms, single, double, or even triple, is one bonding domain. And I like to call them instances of bonding. If there's an instance of bonding between two atoms, whether it's single, double, or triple, it's one instance of bonding, so therefore one bonding domain. Okay, so a bonding domain is any bond at all, single, double, or triple bond. Right, so don't double up or triple up on the bonding domains if it's a double or triple bond. If you see any kind of bond, whether it's a single, double, or triple bond, they're only ever going to be one bonding domain each, ever. Okay, again, any instance of bonding is one bonding domain. Don't overthink this. Okay. Now, the number of non-bonding domains is just going to be our electron pairs, and that's conveniently enough just mentioned right in our table here, right? So our electron pairs essentially, right? So whenever we are looking at electron pairs around a central atom, if there is a pair of electrons around something, as opposed to just a single, double, or triple bond, that's going to be constituted as a non-bonding domain, okay? So here are a couple of, I know they look kind of flat here, right? But these are a bunch of different examples of 3D molecules that look three-dimensional. And again, these are the actual look of these molecules if you were to look at them, as actual molecules, looking at them at the atomic level, right? If we had a powerful enough microscope, we'd be able to look at these molecules and determine that they're not just flat little things that, are not three-dimensional, right? They're very, very three-dimensional. Now, transitioning away from this stuff here is another concept here that's going to help us finalize our lab our covalent molecules lab, known as polarity. All right, polarity is another type of thing to help us kind of define covalent molecules and like what's happening with the bonds here, right? So, plain and simple to start, if you are given let's say any given bond, right? If the electrons are shared evenly across that particular single, double, or triple bond, that bond is going to be considered a nonpolar bond, okay? Whereas a polar bond are where electrons are shared unevenly in a given bond, right? So like, let's say you've got, a couple of different scenarios here where maybe you've got some atoms that, that are sharing things evenly, that's going to be nonpolar. But if those atoms are different and they're sharing things unevenly, it's going to give rise to a polar bond. Well, how the heck do we determine that? How do we determine what atoms are going to be sharing things evenly and what atoms are going to be sharing things unevenly to result in a polar bond? Well, it's pretty easy, okay? Now, when this stuff happens, okay, it results in two ends or two poles where one end has a little bit more of a negative look to it and the other one has more of a positive look to it, okay? But all that's saying is that electrons, although they are actually shared, the electrons just spend more time around the more electronegative atom, okay? And this word electronegative or electronegativity should be a little bit of a reminder to yourselves because we've learned about this a couple of different times now, right? We've learned about it in class twice now. And also we've done a lab centered around it, with that periodic properties lab where you guys had to graph periodic, you had to graph atomic number and electronegativity, right? So it's all on table S there in our reference tables, and we'll take a look at that in just a second. Well, again, how to determine if a bond is polar? Pretty straightforward. So, if a given bond involves two of the same atom, then the bond is nonpolar. That's it. Okay? If a given bond involves two different atoms, then the bond is polar. Okay, so I'll throw a couple examples at you. Let's throw back to an example we already did, right? Let's say we've got O2. Well, the question is going to be, what kind of bond, what is the polarity of the bond between this oxygen atom and this oxygen atom here in the molecule O2? Well, it's two of the same atom across that bond, so therefore it's going to be nonpolar. Okay, well, what happens if we've got an example like CO, for example? Well, what's going to be the bond? What's the polarity of the bond between the carbon and the oxygen in CO? Well, between the carbon and oxygen bond, which is a triple bond, by the way, between the carbon and oxygen triple bond, it's actually going to be a polar bond because the fact that these are not the same atom, right? Carbon is very clearly not the same as oxygen. And that's really it, guys, okay? So conveniently enough, we don't really have to overthink this idea of bond polarity all that much, right? If you're looking at two atoms across the same bond, nonpolar. If you're looking at two different atoms across the same bond, polar. Enough said, okay? However, the more electronegative atom has a slight negative charge, right, like I mentioned, and the less electronegative atom has a slight positive charge, okay? And I'm going to use that word charge sparingly because it's not the same thing as an ionic bond having a positive or negative charge. It's just all based on where those electrons are going to be sort of localized towards, right? They're still going to be shared, so don't get that twisted. It's just sometimes if there's a more electronegative atom, they're going to kind of be shared closer to that electronegative atom and shared a little bit farther away from the less electronegative atom, okay? And again, as we are relatively familiar, our values for electronegativity are going to be placed and listed on table S in our reference table, right? That's pages 10 and 11 in our reference table. Now, when you think of this word polar, polar just simply means unequal distribution of electrons, right, of the charge there. Whereas polar is going to mean equal distribution of the charge of those electrons, right? Now, what happens if you run into a situation where you've got to determine which bond is more polar than another, for example, right? Well, pretty straightforward. To determine which bond is more polar, look at the electronegativity difference between the atoms. The smaller the electronegativity difference, the less polarity. So, if you got a couple different thresholds here. If that difference is less than 0.4, it's a non-polar covalent bond. If that difference is between 0.4 and 1.7, it's going to be a polar covalent bond. But if this difference is higher than that, right, 1.8 or higher, then it's going to lead to an ionic bond, okay? And that's something that we've talked about, obviously, in the past, right? Well, if we're talking bonds specifically and their polarity, well, what about polar molecules? What about the polarity of whole molecules, right? Because bonds are pretty specific, right? Bonds are specific to just two atoms and what's happening in between them. Whereas a polar molecule kind of expands our look here to looking at just, or not just a bond, but the whole picture here, right? Well, a molecule is polar if it has an unequal distribution of electrons, right? The charge of these electrons. Nonpolar molecules have an equal distribution of charge. Well, how do we go about determining the polarity of molecules? It's actually pretty darn simple, okay? Save all of this, how to determine if a molecule is polar stuff for when we're in class. But the thing I want to jump ahead to right here is actually this slide, and it's actually going to be the last slide we talk about in this lecture video here. But anyway, okay, first things first, we need to use our table number 3 in our reference tables, okay? It's also going to be on the very, very last page. I think it's table 3. Did I have that wrong? No, it's table 3, right? So looking still at page 13 in our reference table is table 3, which is titled Common Polar and Nonpolar Substances. It's a beautiful identification table. All you have to do is kind of match up to see if the molecule you're dealing with looks like any of the molecules in those columns, right? So if you have a column, for example, that on the left-hand side, still looking at this, right, is the left-hand side of polar column. If you've got any molecules that look like an XY or an NX3, PX3, H2X, or SO2, for example, right, those are all going to be polar molecules. But if you look at the other column to the right, let's say you've got an X2, right, where any compound with two or of the same atoms, CX4 or BX3 or any of the other examples at the bottom there, right? These are all examples of polar and then also non-polar molecules, right? So as long as you can match up your molecule with anything on this identification table, you are going to be in great shape, okay?